Hello everyone, welcome to another TCSS talk. The talk will be about an hour long and then there will be a Q&A session. Both will be live streamed on YouTube and also recorded. To ask questions, please write them into the YouTube chat or join the Zoom call for the Q&A if you have received the link after registration. And now let me introduce our today's speaker, Professor Clare Gray. Professor Clare Gray is a fellow of Pembroke College and the head of the Gray Group, research group at the Department of Chemistry, University of Cambridge. The Gray Group studies materials for supercapacitors, fuel cells, and batteries. In today's talk, Professor Gray will be speaking about battery technologies and development of methods that allow studying processes in them while they are operating. Please welcome Professor Gray. Professor Gray, the stage is yours.
Thank you very much. I'm delighted to be here, at least virtually, and I hope everyone is well, wherever they are, and surviving. So I'll just share my screen and then I'll talk a bit more. So I hope that you can all see me, or see the screen rather. And if I put it in full screen mode, then that should work. Just let me just sort myself out. So is that okay?
Yeah, great.
Great. So what I wanted to do today was talk about a very, I think, very important activity and research area for the world, and that's really thinking about how we make impact by doing our research for reducing carbon and trying to achieve technologies for sort of a zero carbon society. And what I hope also today is I can illustrate that even if the results or the things that I'm working on, my batteries and my supercapacitors, are applied and they have relevance to you in your lives in the sense that we're all using laptops and mobile phones, there's some really interesting fundamental research questions which require advances in chemistry, physics, and engineering and material science, and touches on ideas and things that you might be thinking about in the research you're doing and the not just the research but the learning that you're doing as undergraduates here in Cambridge. And I'm sure that most of you are quite familiar with what a battery is, but I thought I'd still go over that and just introduce what a battery is, why do we care, what are some of the challenges, what are some of the new directions, and then talk about my own field, which has really been around using NMR spectroscopy to probe batteries. But I also want to sort of at the same time introduce other methodologies that we use. And hopefully you can then ask me some questions on stuff that wasn't explained as clearly as maybe it should have been. Anyway, so the rocking chair battery, or the Sony rocking chair that really is in all of your mobile phones, was originally put together in 1991 by Sony, and it was called a rocking chair battery because the lithium ions go backwards and forwards between lithium cobalt oxide and graphite. And so on oxidation, you oxidize the cobalt 3+ to 4+, and you pull the lithiums out. They go through a non-aqueous electrolyte, and then they get nominally intercalated safely into these graphitic anodes. And the point of this slide really is to illustrate that it's much more complex than just having a cathode material and an anode material. You've got to think about an organic electrolyte that's going to be stable enough in the very reducing potentials of lithiated graphite. So that's almost as reductive as lithium metal itself. It's only 75 millivolts higher than lithium metal at its most reduced stage. You've got to have current collectors on aluminium on one side, copper on the other side. And then when you make the whole electrode, you've got to combine it all together, essentially with carbon black to get the electrons in, a binder such as a polymer to hold the whole thing together as you expand and contract the materials as the lithiums are coming out. And then you've got to have porosity so that the lithium ions can get in via this organic electrolyte. And all of this has got to last for the many times that you want to cycle your battery, whether it's in your phone or whether it's an electric vehicle where it might want to last for 7 to 10 years, or on the grid where this might be 20 years. And so this is a real chemical, physical, material science and engineering challenge to get this to work. And in some ways, it's amazing that it really does. And so then, of course, why is it important? Well, other than the portable technologies revolution, which was really enabled by the lithium-ion battery. If we didn't have batteries, we wouldn't really have the ability to sort of access data in the way that we just are so reliant on now. But moving forward, the challenges really are, how do we reduce carbon emissions? How do we reduce pollution? And batteries do this in two ways. One of this in terms of electrification of transport. So we already have batteries in cars, but what we want to do is to try and think of a battery that would be cheap enough and light enough for a lorry or a truck, so that we could electrify the whole transportation system. And then the really challenging thing is to do storage on the grid. And there we're talking about batteries that compete with Dvornik, which I can never pronounce, but this is the mountain in Wales where we pump water up and down. And that's one of two pumped hydro setups in the UK that is used for balancing supply and demand. And batteries have higher energy densities, but it is still the sizes of dams and mountains that we're thinking about. And so you think about, how do you go from these little batteries that you're used to and construct things on that scale, and things that will last for sort of many, many years. So for me, this is the sort of ultimate challenge, that how do we come up with an energy storage system of that scale? So the next thing that's really important to appreciate is that since the development of the first lithium-ion batteries, as said back in 1991, battery energy density, so that's the amount of energy per unit weight or per unit volume, depending on the application, that's gone up by about a factor of 3. The prices have come down more than factors of 10 now, partly due to engineering, due to mass manufacturing. But if we really want to do a lot better, we've got to come up with new radical approaches for this. And this is sort of the role that we in universities have, is trying to shape that next generation of technology and doing the fundamental science that's needed to do that. So this then has to be done within the context, though, of safety. And this is the Samsung phone that had a number of incidents a year ago, and that was only associated with trying to pack 5% more energy density into the same volume. So this is just to remind us that, of course, John Goodenough, Stan Whittingham, and Akira Yoshino won the Nobel Prize sort of last year in 91, and that was for basically for the work that put this lithium cobalt oxide battery together. But we need to move beyond this pioneering work for the next generations of technologies. So I just thought I'd spend a few minutes and discuss, why do batteries fail? So they do that for a number of different reasons, but they have some of the same sorts of origins. And one of them is an organic chemistry problem. And that's simply that you have an electrolyte, and yet you're asking this electrolyte to operate at very low potential, so down close to lithium metal. And there is no electrolyte, so there's no organic material. And of course, water is definitely not stable, those sort of voltages. Everybody knows that if you plonk a bit of lithium or sodium into water, you generate hydrogen very quickly. And so the only way that batteries survive is you form a passivating layer on the surface of the graphite. It's called the surface electrolyte phase, or SEI. And this forms a passivating layer in the same way that you have rust on iron, or the copper metal is typically bluey green, not because copper is that color, but because the passivating layer is, and that prevents further reaction. So the same thing is going on in the battery. But if this passivating layer has to stop the electrons going through, but it has to still allow the lithium ions to go through. And so if you, for example, use your mobile phone in too hot environments, or you insist on using your laptop on your lap, which I'm doing right now, then this SEI degrades, and you start consuming more electrolyte, and you build up internal resistance as well, and so gradually the battery fails. So that's sort of a major mechanism. And then you have this idea I talked about before, that particles expand and contract, and they can crack, and so you can lose electrical contact. Or there's another idea that when you make a material, it's typically made in its stable thermodynamic state. But when you charge it, in this case, you take lithium cobalt oxide and you pull out 50% of the lithium, this material is no longer thermodynamically stable, it's metastable, and it's metastable towards a cobalt oxide and generation of oxygen and obviously heat. And it's that oxygen then that can react with the organic electrolyte and cause these fires. And so it's really a sort of game of beating metastability. And then there's a whole slew of different decomposition mechanisms, which I can happily talk about, which is something I do a lot of research on. And then, of course, there's cost. So cobalt is expensive and is limited in its resources. So this brings me nicely to the thinking about resources, that as the world is building these gigafactories to supply the next generations of electric vehicles in particular, there's a phenomenal amounts of lithium, cobalt, and nickel that are being used. And so these are the sort of projections for cobalt. And over on the right is the amount that's actually being produced in the DRC, so the Democratic Republic of Congo, and you can see that there's, these are the same orders of magnitude as being projected as actually being produced in the Congo, and that's even not mentioning some of the environmental and human rights issues in terms of mining in the Congo. And we think about lithium, there's enough lithium in the world, but this is a picture taken by me in Chile of the Atacama Desert. So these are brine lakes, and what happens is the companies pump the brine out, and then they evaporate it in ponds to separate the components, which are sodium chlorides, magnesium chlorides, and lithium chlorides. And then they separate them. But this massive amount of mining is impacting both the people who live nearby in terms of water supply, and also the animals and the birds that live there. And these are the flamingos that eat the algae and the ponds, and that's where they get their pink colors from. And so they're sort of being impacted by this. So this is just a sort of statement that as we increasingly build more batteries, it has to be done in a sustainable way for it to be able to even imagine how we're going to do this for electric vehicles, let alone for grid storage. So what are some of the current directions? Well, the sort of move towards lithium cobalt oxide to lithium nickel oxide was motivated by this cost issue and the mining issues with associated with cobalt, but also motivated by higher energy density. So you can get more lithium out than you can in the lithium cobalt oxide in a stable fashion, but it's still not stable enough. And so what the field has come up with is this whole slew of different compounds where you take the cobalt or the nickel and then you mix in manganese 4+ to make it more stable. Manganese is a more abundant element. You put in aluminium to increase the stability. And as a result, this is the material that's in the current generations of cars. And this is the next generation material. It's so-called NMC, so nickel, manganese, cobalt, 811, where 8 stands for 80% nickel, 10% manganese, and 10% cobalt. And so this is the material that we work on to try and understand whether it's really fit for purpose and how it degrades and how to mitigate that. So there's some sort of interesting materials challenges. And so this is for the sort of people doing material science in the audience. Originally, we started off with this so-called single crystals, and they're not really single crystals. They're structures where the primary particles are just not agglomerated. And then new synthesis routes came along where we had these large so-called meatballs or raspberry structures, depending on which group you come from, where it was made up of lots of small primary particles agglomerated to make these secondary particles. But when these particles are cycled, the materials expand and contract, and you get a lot of cracking. And so the push now is to try and do new syntheses so that you can make single crystal 811. And as a result, Jeff Dahn's group, who's a group in Canada, has come up with this battery that he predicts can last for years and years and years, and if made out of these single crystals. Now, there are many other reasons why these batteries fail, but at least based on this material, he made the prediction that you could design a battery that would last for 25 years, which is another way of reducing cost, because it's one thing about how much you pay for the battery in the first instance, but if you're having to replace it every 2 years, then that adds obviously a lot more cost. And maybe in your mobile phone you don't care because you want the latest Apple phone or Samsung or whatever phone you want, but if it's a grid storage battery, you really do care. So what can we do to improve it? Well, the material that's been around for a lot is silicon. And silicon, it's one down on the periodic table, but it reacts very differently with lithium than does carbon. And so one lithium reacts with 6 carbons to form the N-member compound LiC6, while a silicon can react with almost 4 lithiums to form Li3.75 silicon. And so that gives you almost a 10-fold increase, or more than a 10-fold increase, in both volumetric and gravimetric capacity. And so it would be really exciting if you could get silicon to work. And that gives you an overall sort of at least 50% increase in energy density on your battery if you look at the full cell. The problem with silicon is the problem that I talked about before, and that's the idea of this electrolyte decomposing and forming SEI. And so this is a picture from our work where we have an original electrode structure, and at the beginning, this is the pristine material. You can see it's holy and porous, and we're doing that because this material expands by about 300% when it reacts, and that's simply because you're adding so much lithium. So you need some space to allow it to accommodate that expansion. But then as you react further, you get this electrolyte decomposition, and you just basically get this mushy mess of decomposed products. And by the time you've cycled 60 times, you can see it's just become this dense mat. And the capacity, so we measure the capacity in milliamperes per gram. So amp time, so current times the time we do it for. So that's the amount of and the energy density per unit of gram, that's of density. And you can see it's dropping significantly only over 60 cycles. And that's just literally the resistance of getting the lithium ions through this junk. So what we did was to come up, well, we've been thinking about new strategies to overcome that, but this is still a challenge, even though Tesla is starting to put a bit of silicon in their cars. So let's think about, where do we go next? And an obvious place to move beyond lithium is to move to sodium. So it's almost sort of drop-in technology, but sodium is bigger than lithium. So as a result, the energy density is lower. And even more surprisingly, or maybe not, but sodium you can't intercalate into graphite. You can intercalate lithium, you can intercalate potassium, but sodium is just the wrong size. And so instead we have to think about new anode materials. And this is an example of a disordered carbon that will react. And I'll come back to that later. So let's sort of think more outside the box. What about the rest of the periodic table? So the next one along, obviously, is magnesium in terms of size. And, you know, for the chemists amongst you, in many ways, magnesium behaves quite similarly to lithium, except, of course, it's got a 2+ charge. And the advantage of a 2+ charge is that you can find a material that needs less space to hold the magnesiums. And so you could imagine this is a layered compound with lithiums, but if you had magnesiums in there to compensate charge of the transition metals, you'd only need 50% of them, which means if you had the same number of magnesium, then in principle, you could pull more electrons out of the compound. But the problem is that magnesium is, because it's highly charged, it's also extremely well solvated by the ions in solution. So it's very difficult to pull the magnesium out of solution and put it into the material. Or it's very difficult to plate it onto the magnesium surface and do the stripping and plating. And then the next challenge is, how do you move an ion through a solid? And if it's a 2+ ion, the activation barrier of the jump is up. And so the only materials that really work very well are the sulfides, and that's because the sulfides are more smushy electron density, and so the low activation barriers are lower for transport. But you can see this is the magnesium battery, and it's operating at 1 volt. And a typical lithium-ion battery operates between 3.6 volts and 4.3 volts. So we've taken a hit of a factor of 3 on that. And this is some examples of some work with myself and Professor Dominic Wright, and former PhD student Evan, who was looking at this issue of how do you strip and plate magnesium. And so what Evan did was to synthesize a new version of salt. And so the typical salt in a lithium-ion battery is LiPF6. And so what was surprising was that no one had made the magnesium PF6 before. And so Dominic Wright and Evan were able to do this. And then we were able to make an electrolyte and look at the stripping and plating. So this is the original magnesium. This is the blow up. And what you're seeing are sort of globules of magnesium on the surface. And this is good news because it's not dendritic. And so you don't have the safety instance I'll talk about in a minute. But the bad news is if you put it together in a full cell, you can see this very large difference between discharge and charge. And this is a very large overpotential of more than 1 volt. And that's because of the difficulty of plating the magnesium and also inserting the magnesium into the electrode structure. So what are the real paradigm shift changing technologies that could really make an impact? So if we really want to sort of look at those, we want to go to really cheap elements. So we look at sulfur, we look at oxygen, and we could do a lithium sulfur battery, which is a reaction of lithium and sulfur to form Li2S. The problem with that, and this is, this is basic inorganic chemistry, is that to go to Li2S, you go from S0 to S2 minus, and you go via these polysulfides. So sulfur is a ring, it's got sulfur SS bonds, it's S8, but you've got a slew of compounds in between, like two, so S2, 2 minus, and the 3 members things, and they're all soluble. So they dissolve in the electrolyte and you end up with redox shuttle processes. And so it's very challenging to sort of get that to work. The thing that we work on a lot in my group is in the lithium oxygen battery. And this is the only technology that has the same energy density of gasoline or petrol. And so if we could get that to work, it really would be a game changer. And this is something where you react with lithium plus oxygen to form lithium peroxide. So you go via oxygen, via superoxide to peroxide, but you do that by, in the same way that you would in a fuel cell. So you have a carbon electrode that supplies the electrons, the oxygen comes in and you form this, and then on the surface of these carbon forms, you form the peroxide. And the challenge is, I'll show you in a pitch in a minute, is that you form these dense mats of lithium peroxide, and lithium peroxide is an insulator. And so when you try to charge the material, it's very difficult to get the electrons in to the material to oxidize the peroxide back to oxygen. And so there's a lot of work globally to try and solve this problem. And one of the sort of practical ways of doing this is to use what's called a redox mediator. And so this is an example of a quinone. So you can take a quinone functional group with carbon oxygen double bonds, and you can reduce them, and you can put them, and you reduce them on the carbon electrode, and then they go on and they react with the oxygen. So this is the picture of the oxygen here. And then you can essentially get the chemistry to work in solution so that you can build up much larger deposits of lithium peroxide. And then you can come in with another redox mediator, tempo, which is a nitroxide, and you can then use the nitroxide to oxidize the lithium peroxide, and you can reduce the overpotential. And this is work of ours fairly recently, where we were showing that you could also introduce water, which would improve the solubilization and improve the capacity. And we can also play around with using peroxide versus lithium hydroxide to further increase the capacity. So what about the ultimate in safety? Let's get rid of that organic electrolyte. And this is an example of a ceramic composite. And this hopefully is interesting to some of you doing materials science. So you can do a technique called spark plasma synthesis, where you can fuse it all together and you can make a material. Here's the electrolyte, here's the cathode, and here's the anode. But you can see you've got to get the lithiums across all of these multiple grain boundaries, and the materials are sort of expanding and contracting, and you've got to get the electrons in. And so there are a lot of challenges for this still to work. And so as a result, there's a lot of people using polymers instead as sort of hybrid solid state batteries. And finally, sort of thinking outside the box, this is the ultimate thing where you say, okay, let's forget the idea of a box that defines how much material you have. Let's have an electrochemical cell, and let's have oxidized and reduced materials, and then we flow them in when we want them to do the electrochemistry. And that allows us sort of decouple size or materials from the electrochemistry, and then that ultimately is stable. So this is sort of a cool area that we're looking at next. So what I want to do now is transition to the work we're doing and give you a sense of what we're doing, try and get through as much as possible. But the work that my lab does is in addition to sort of making materials and making batteries, is to try and develop new methods to understand how these things function and fail, and to try and do this in situ. And we're sort of interested in structures all the way through to how you put the electrodes together and how different processes work at different length scales and time scales. And as I said, I'm trying to do this in situ. So while this is operating, because it's an efficient way of doing it, it allows us to capture metastable products, and it allows us to capture things that maybe don't survive if the battery is pulled apart. And it's not so easy just to take a normal battery and shove it in an NMR probe, because for the simplicity is NMR spectroscopy, which is the major method we use, is a technique where you excite the nuclear spins using rethink it. And so we've, over the years, developed this whole metrology and built new NMR coils to do this. And so let me know if my internet is dying. I won't see it, there's a problem. And so I'll just walk you through what we've done. So first of all, you've got to think about the materials that you're studying, and each of the materials have different NMR responses. So we have metals, we have diamagnetic liquid materials, they could be liquids, they could be solids. And then we have to worry about the different interactions. They could be electrons, they could be not electrons. So we have to develop those methods. And then we have problems that if we have, is in this picture here, you have a battery shown here, and then it's connected to the battery cycler shown here. That acts as a pickup circuit for RF. And so you can see in the tuning circuitry, this is literally the noise coming in from the environment of the NMR machine. So you have 50 hertz from AC, and then you have radio stations, and that all contributes to it. So we have to filter all of that out, and then we have to do safety issues. This is a battery that unfortunately blew up because it got overheated from the RF. So all of this has to happen. So what we do is we make these little batteries, and these are so-called plastic bag batteries or coffee bag batteries, because we use the same technology as people use to seal coffee. So this is a plastic laminate. So we laminate it with a sealer, again, the same sealers that people use to seal smoked salmon or coffee or make credit cards. This is the mesh here, and these are the current collectors. So this is the copper on one side, this is the aluminium on the other side. The white thing is the separator that separates the cathode from the anode, and we build them small enough to sit in these 1 centimeter coils. And we've then developed little motors so we can control how we do the tuning automatically. And we do that because as you cycle the batteries, sometimes they become paramagnetic or metallic. And so the tuning circuitry changes, so we can do all that remotely. And then we have new designs of batteries which allow us to deal with more air-sensitive materials and things like that. So a lot of work. So I just want to illustrate a few examples. And so the first example is of a supercapacitor. So these are materials that, or devices that discharge and charge very, very rapidly. So this is a so-called Ragone plot, where you plot power versus energy. And so this would be a battery where you have a focus more on energy density, while as a capacitor, like a dielectric capacitor, has very little energy density, but has much higher power. And so these supercaps bridge the two. And what they're known as supercaps or electrochemical capacitors, and they consist of these carbons that are highly porous, and then when you charge them up, you store charge in the form of a double layer. So this is charged positively, then you store negative ions on the carbons. And this is an example of the type of structure that you have. It's very hierarchical. They're activated carbons made out of coconuts. You activate it to get these sort of holy structures that are good because you allow the materials to go in. And this is a binder that's pulling the whole thing together. And they're in your mobile phones. They're the reasons you can have a flash, so you can discharge very fast. They're in the emergency exit systems of the Airbus, the new Airbus plane. So they activate the chutes going down. So it's when you want really rapid power. And surprisingly enough, when we started in this field, people hadn't worked out how these compounds actually worked. And so these compounds or activated carbons consist of sheets of carbon. They're very graphitic. And if you do a thought experiment and you say to yourself, at 0 volts, I'm going to charge it positively. How do I store charge? Now, I said it was in a double layer, but it's a bit more complicated, or not complicated, but it's more really to do with how ions go in and out the pores. And so you can imagine that if you have a positive surface, you could store charge by kicking out positive ions. or you could store charge by bringing in negative charge for charging compensation, or you could simply just swap and do ion sorption. And so what we did over the years was to actually develop this whole metrology to answer the question of how these things charge. And so what you're watching here is a supercap, and you're watching the fluorine NMR. So I'm looking at a BF4 minus anion, so the fluorine signal of this anion that's in an electrolyte comprising an ammonium ion and in acetonitrile. And I'm watching the fluorine as I'm charging this thing positively and then negatively. And this is the signal of the ion that's actually in the pore. And what you're first of all seeing is a shift to the right, and then it shifts to the left as you're charging up positively. So the shift to the right is a ring current, and is exactly the same thing that you see when you do NMR spectroscopy of benzene. And so in benzene, you have a very large shift of about plus 7.3 ppm, and that's due to the ring currents in these benzene molecules. And because the protons are here, you get a positive shift. And so those of you who are sort of following, this is actually a negative shift. And the reason it's negative is that the ions are sitting on top of the graphene sheets. So they're not single rings, they're really more graphenic shifts, and they're more like these sort of coronines or dicircumcoronines. And so this is showing you a DFT calculation, which is predicting that if you're sitting on top, then you get a negative charge. And so this is now an experiment where we're charging both positively and negatively, and we're quantifying the intensity of this signal. And based on that, we can actually show that when you charge positively, you have an ion exchange mechanism where anions go in and cations are kicked out. But when you charge negatively, actually only the cations go in. And that's because they have a preferential adsorption with the carbon. Okay, so what about this shift of this peak? So it's going backwards and forwards. So here, this is when the carbons are the most aromatic. But when you put in electrons or you put in holes, you reduce the aromaticity, and so you get a shift. And so you can understand things about the electronic structures of the carbons as well. Okay, so what else can we learn? I just wanted to touch on some NMR now studying sodium NMR, and we're now doing sodium NMR for the reasons I touched on before, because of the sodium-ion batteries. And so I mentioned the fact that you can't use a graphite for the anode, so instead you use this material called a hard carbon. And again, so we're now using NMR spectroscopy to look at the discharging of the hard carbon. And what you can see here is a signal, two types of signal. One is around 0 ppm, and then you get this very large shift to more negative ppms, getting close to the signal of sodium metal. And from this very simple experiment, we were able to prove that this low voltage process was due to sodium sitting in the pores of this material, forming so-called sodium metallic pools that gave you this metallic signal. And so by doing these experiments, we can really understand not only about the structures, but also the electronic structures of these materials. And this is an example where we're looking at tin as an anode material. I just want to turn the circle around and talk a little bit about the silicon. And so this was the first example of our work where we really figured out what was going on with silicon, and we looked at the type of structures that were formed in this material. But what was interesting was when we looked at model compounds and we asked the question, what do the stoichiometric compounds, what do the NMR signals look like? So this is now lithium NMR. We got very different signals than we did when we made lots of batteries and we examined their NMR. And this is and then in the in-situ NMR, we actually saw this peak at negative ppm, which we didn't understand until we let the battery sit for a long time. And so this is discharging. So we're putting lithium into the cell. These are forming lithium near clusters. And at the end, at this final compound, Li15 plus Li15 Si4, you ended up with a negative peak, which we never saw in any of the model compounds that we'd made in order to understand that. And what turns out is what we make is this lithium excess material that is very unstable, and it reacts with the electrolyte. And so the signal disappears if you sit here and you wait. And so what you're watching in obviously sped up real time is the reaction of this compound with the electrolyte and the degradation that is to this date really preventing massive use of silicon in the field. So I want to talk now on some of the work we've done on safety and dendrites. So in the days when we all, could take more planes, the Dreamliner was a plane was introduced by Boeing a few years ago, and it ended up being grounded for at least a year because they had problems with the lithium-ion battery. And the thought was that this was due to lithium dendrites. And so you can't actually use lithium metal, you use graphite instead. And the reason for that is as you cycle backwards and forwards, you form these mossy structures on the surface, and they can eventually become dendritic. You've got short circuits, you get heat, and then that's what causes some of these fires that I've shown you. And if you do the same thing with graphite and you charge it too fast, you can also plate lithium and have the same problem. And so what we recognized now a while ago was that the same issue you have about getting the RF through a can in a battery has the same problem through lithium metal. And so you can't just detect the full amount of the lithium metal, but you can actually detect these dendritic structures. And you can quantify how much you can penetrate the RF through via the so-called skin depth effect. And for lithium metal at the fields we're using, so this is 77 megahertz, it's a 200 megahertz field for protons, we have a penetration depth of about 15 microns. And so what we did was to use that to sort of then quantify how many dendrites are formed. And so this is lithium metal demonstration thing where we're looking at a symmetric cell. So we have lithium on one side and lithium on the other. We go backwards and forwards at increasingly higher currents, the constant mass of lithium, but you can see this is the lithium metal signal, and you can watch it grow as the surface area is increasing. Therefore, the penetration of the RF is increasing due to these dendrites. So watch the dendrite signal coming up here as you increase the current. At the same time, watch the signal at 0 ppm. This is the signal due to the electrolyte that's decomposing to form these SEIs compositions. So you're watching the growth of a dendrite and at the same time form this passivating layer over it. And this movie here is just to show you that dendrites, are even bigger problem for sodium. Okay, so why do dendrites grow? So in order to look at that question, we use magnetic resonance imaging. And the nice thing about magnetic resonance imaging, you can do so-called chemical shift imaging, and that's something that's used in functional MRI in the medical field, where you can look at specific frequencies. And so this is an example of the electrolyte and the metal. So the electrolyte's in red, and on the right is a chemical shift image where you've got the shift versus distance. And this distance here is the distance between two lithium sheets. And so as I flow current, the lithium ions move in this direction. The PF6 minus counter anions move in this direction. The lithium ions deposit, but because the PF6 minus anions can't, you build up this concentration gradient. So that's what you're seeing in red, is the beginning, and then this is the end. Now watch the lithium. So as the lithium is starting to grow, first of all, it grows near the surface. And then when the lithium electrolyte concentration drops to 0, the dendrite starts to grow. And you can see that more clearly in the CSI. Here's the mossy structure, and there's the dendritic structure. Now, why does this happen? It happens due to a phenomena quantified by the so-called Sands time. And the Sands time is when this concentration of the electrolyte near the electrode is depleted. And at that point, you get an electric field or a space charge that pulls your dendrite away from the current. And we can predict that based on knowing the diffusion coefficients for lithium and PF6 in our solution. And we can see that it all works very well until you get to these high currents and got it totally the wrong way, until you get to very low currents. And at low currents, you would predict actually that you would never get this depletion, and yet you still get the dendrites. And this is what is showing in this picture here. The movies for some reason isn't working, but you can still see it's forming this dendritic structure. And the reason for that is this wretched thing, the SEI, the passivating layer that I just keep on going on about. And that's because when it grows, it's this inhomogeneous mess, and it results in inhomogeneous transport through it. And so you get hot spots in it. When a hot spot forms where maybe it's thinner, then the dendrite starts to grow. And so the challenge here is to really work on the nature of this SEI to stop dendrite formation and to enable lithium. I just wanted to touch on the fact that I talked about solid state batteries, and one of the reasons why people like solid state batteries is it allows you to use lithium metal. The problem, though, is even in these very dense ceramics people are using, lithium just forces its way through the dense ceramic. And this is what you're seeing here, a web of lithium around a particle of LSO. It's a lithium lanthanum zirconate. And we can track these processes of MRI as well. Okay, I just wanted to touch on one very new area in my lab. So we're in the process of installing a new machine. It's called a DNP machine, or dynamic nuclear polarization. And this is a technique where you make use of the fact that electrons have a gyromagnetic ratio that's 1,000 times of that of a nucleus. And so if you do ESR versus NMR, it's 1,000 times or more sensitive. And so what Overhauser of the NOE predicted back in 1953 was that you could actually use the polarization of electrons in a metal. So those of you who've done some band structure know that at the Fermi level of a metal, you have unpaired electrons and they have spins, and you can use those spins to polarize the lithium metal. And so Overhauser predicted this in 53, and Charlie Slichter actually demonstrated it the same year. And so the first measurement of dynamic nuclear polarization was on lithium metal. And so this was largely forgotten about between 53 and 2020, when we decided we would go back and think about, could we use this to study our batteries? And so we, in the sort of intervening almost 70 years, we have much higher fields, but actually for this, it's not necessarily an advantage. So we were able to replicate the Overhauser effect for lithium metal in our dendrites, and we get modest enhancements of signal. So what you're looking at in blue is the lithium signal. And then when you turn the microwaves on, so the microwaves are tuned, so they hit the electron resonance, you get a signal enhancement of, in this case, about 8 times. And so it's interesting, we can do things with it. And what is really interesting is we can then transfer magnetization from the electrons to the inorganic components that are on the surface of the lithium metal, so the inorganic components of the lithium SCI interface. And so this is a really nice technique we've just come up with to look at metal insulating interfaces, and buried interfaces and their structures are to characterize one of the sort of challenges in the field in general, in both chemistry and physics. So I just wanted to give you a few more flavors on the work we're doing. So this is the work we're doing via the Faraday Institution. So the Faraday Institution is a new institution in the UK that's meant to bring together new people to attack the challenges in batteries. And for, I lead the UK's battery degradation project, and we have a lot of different universities where we apply lots of different methods to understand how batteries degrade. And the material we're looking at is this NMC, so nickel, manganese, cobalt 811, and graphite on the other side. And my group, for example, uses NMR spectroscopy, obviously, but we also do NMR, SEM and TEM, and we do different DEMS, which is a method of looking at gas evolution from batteries. We do some neutron diffraction and XPS and things like that. So I'll use a whole variety of different techniques to look at these systems. And so this is just one example to give you a flavor of the sorts of things we do. This is the this is the diffraction rather of NMC 811. So this is the cathode material. So together with colleagues at Argonne National Lab in the US, we've built a cell that allows you to shine X-ray beams through the cell while the battery is cycling. And so what you're watching is a diffraction pattern as you pull lithiums out of these materials. So this is the so-called 003 peak, which measures the spacing between the layers. And you can watch the layers, they expand slightly and then they collapse. And this is shown more clearly here. So here's the expansion and the collapse as a function of how much lithium you remove from the material. So let's think about why this might be important. So here's the layer again. Here's the picture of the expansion and then the collapse of the collapse. And the collapse occurs at about 0.65. But in point of fact, the actual lithium layer, so this is the lithium layers here, that happens at about 0.75. And so the question is, if the layer collapses, what is the implication for how fast the lithium ions are moving in this structure? And that's obviously important for how the rate of the battery. So what we do, not surprisingly, to understand this is NMR spectroscopy. So here's the NMR now, and this is not in situ. This is where we make lots of different batteries and we take them apart and run them individually to get better high resolution spectra. So here's the broad signal for the first, the original material, and this is the one at the top of state of charge. And so you can see this battery is operating at somewhere between 3.7 and 4.4 volts. Now, this is a whole talk in itself, but I spent a lot of my career in trying to understand what causes shifts. And the main sort of take-home message is that if you have transition metal ions, they generally have unpaired electrons, and that obviously depends on how many electrons there are in the T2G and the EG orbitals. And so, for example, if you have nickel 2 plus, nickel 2 plus is D8, so there are electrons in the EG orbitals, and they point towards the lithium. And it's not as simple as all the electrons just sitting on the nickel orbital. If you have a covalent bond, some of them are transferred from the nickel through the lithium. And it's these transfer electrons through bonds and also through space that are responsible for magnetic couplings and for magnetism. But we're operating in the regime where things are paramagnetic, but you still have the effect of the unpaired electrons. And this is what's giving you these broad, very large shifted signals, because you're seeing a whole variety of different local environments. But at the top of charge, I've oxidized. When I pull all the lithium out, nickel 2 plus goes to nickel 4 plus. And for those of you who've got your periodic tables handy, nickel 4 plus is D6. It's low spin D6, so it's diamagnetic. And so when you're at top of charge, all you see are the manganese ions, and the manganese 4 plus is D3, so T2G3, and that has very large shifts. And what you can see is the lithium near 1 manganese and 2 manganese there. So that's just what I've just told you. But the question then is, what's going on here? Now, again, for those of you who've started to do a little bit of NMR spectroscopy and maybe even doing part 3s, will come across the idea of motional narrowing. And so if you have ions hopping from site to site and they hop fast enough, you don't see the individual environments, you just get an average. And so what we're watching here is when you go from even from 40 degrees to almost 70 degrees, you get a narrowing of the signal as the lithium ions are hopping. And we can go through sort of analysis of this and simulate things and simulate all the spectra as a function of state of charge. And we can extract, depending on the model, hop rates for the ions in the structure. And what you see is between about 0.25 and 0.75, you get quite rapid lithium ion conductivity, and you get moderately low activation barriers for transport. So this is all good if you want a fast charging battery. And this also agrees with electrochemical measurements we do. And so then you go back to this question that motivated it. What happens when you get this layer collapse? And remember, the layer collapse is happening at 0.75. That's in the same region where you get this reduction in lithium mobility. And so the sort of the take-home message from a sort of car manufacturer's perspective is, if you want a high-rate battery, then you need to cycle between 0.25 and 0.75. Okay, so I want to just end by telling you a little bit about our work on making even faster materials with even faster mobility. And so if you step back and ask the question, how do we do this? Well, we obviously want materials with holes, so that allows the lithium ions to move through. And some of the most holy materials are these so-called rhenium trioxide structures. So they're perovskites, but they're missing the holes in the center. But the trouble is, if once you try and put lithium in them, the layers, the octahedra rotate and they clamp down the lithium, and so you don't actually get very rapid lithium mobility. And so I'm not proposing that you make a rhenium trioxide battery. I'm just literally using this to illustrate the structural issues. And so what the solution is to think about, how do you stabilize these open structures to stop that happening? And nature does that in a number of different ways. You can have these shear structures in for example, TiO2 when you reduce it, or where you get a shearing of these blocks to form these octahedra. So this square is looking down an octahedra, and you can see, instead of it being an edge-shared octahedron, so this is a corner-shared octahedron here, it's an edge-shared after the shear. And what that does is it gives more stability to the structure. And when you're in a niobium oxide, in order to compensate the the missing oxygen, you actually have to shear in multiple directions to actually get blocks. And so this is an example of a whole variety of different niobium oxides, where depending on the ratio of oxygen to niobium, you can get different block sizes, and they have different electronic structures. The other way to do it is via so-called bronze, and they're called bronzes because they have bronze-like colors, is to take 4 of these units and rotate them around. So this is the same unit here, but now I've rotated it by 45 degrees, and you can see then that you've got the 5-membered rings instead of these 4-membered rings, and you can form a structure called TNB205 that has this sort of bronze structure. So one of my former PhD students, Kent Griffith, spent a lot of time looking at lots of different materials, and he found that some of these niobates were really very high rate, even when there were these very large particle sizes. And so then he went through and he looked at a whole variety of different titanium niobates and tungsten niobates, and identified 2 tungsten niobates, one that was a block structure and one was one was a block structure and one was a bronze structure, and that he then tested them in these battery applications. And you can see they have very large particle sizes. So these are so-called single crystal morphologies, where you don't have these multiple, they're semi-agglomerated, but not in the same way I was showing you before. And then what we can do is to test them against lithium metal and test how fast they cycle. And so this is an example now for the niobium 16 compound. So when you cycle slowly, you get a capacity of about 250 milliamperes per gram. But when you're cycling up at so-called 60C, you can still see that you get quite a reasonable capacity. So just to explain these notations to you, 1C is the battery notation for taking a battery and charging in 1 hour. So C/5 is 5 hours, and 60C is a 1-minute charge. So what we're showing is that even at 1-minute charge, you're getting reasonable capacity. It's not perfect because it's not engineered, and actually it's the lithium metal that's causing us a problem. But you can see at 20C, we're getting quite a respectable capacity. And so what we then do is to ask why, and we can use a technique called pulse field gradient NMR spectroscopy to quantify how fast lithium ions move. Happy to take questions about this, but the bottom line is they move with quite low activation barriers. So I mentioned in the previous one, the activation barriers for lithium hopping in the cathode about 0.3. Here we have activation barriers that are more like 0.1 to 0.3, so lower, and relatively fast diffusion coefficients. And they're faster than the best in class solid state conductors, not as fast as lithium electrolytes, but still really good. And so that was enough to sort of get this work into Nature and then make us think about, why this happens. And this is just to illustrate, if you want to build a battery that cycles fast, just how good does it have to be? So if we think about a battery that we're charging in 1C, so we're charging in an hour, and we have diffusion coefficients of 1 × 10⁻12, it means in 1 hour, the lithium ions can move about 150 microns. So if we want to charge in 20C, so 180 seconds, which I think is a reasonable criterion for fast charging, although you might argue 60C is, then you really need, if you, for example, go for 60C, then if you have 10⁻12, then that'll get you 19 microseconds. And so our materials are somewhere between 10⁻12 and -14 rather. So we can go about 10 microns in a 60-second charge. And so that's why we're able to use these large sort of particles. And this is the comparison of the sort of the next best material, which has a diffusivity of 10⁻15. So that's why this material has to be nano-sized. So anyway, we do a lot of work in trying to understand the why this works. And this is some work of Can Kosa and Andrew Morris looking at the theory of these things, trying to understand where the electrons go. One of the important things is the electrons go into bands that go all the way down these tunnels and give these compounds metallic conduction, which is another reason why they work very well. So in order to move lithium ions and to get you need to get lithium ions in and also electrons. And so this is an important part of the good materials performance. And so the bottom line is these are really very good performance, and we've just spun out a little company to try and see if we can enable their use in fast charging batteries. So with that, I just want to tell you one short story, and that's about our redox flow chemistry. And this is because I think this is, one of the sort of ultimate batteries, I think, where we need to think about the next generation of much bigger batteries. And it's this idea of not being constrained by the volume that you have your material in, but being able to have an electrochemical cell that's separate from the tank that stores your oxidized and reduced materials. And the current sort of semi-commercial systems are vanadium-based ones, where you can have vanadium 2+, 3+ on one side and vanadium 4+, 5+ on the other side. And that's good because if you have any so-called crossover between one side to the other by the membrane, it's still vanadium. But vanadium is toxic. Vanadium is expensive. It's not its abundancy on Earth is not brilliant. So there's the Earth abundance. And so there's a lot of work now to think about different materials. And so I thought I'd put this in for those of you who are interested in organic chemistry. There's a lot of work on trying to find organic molecules that have redox activity. And I already talked about quinones as redox mediators, and I'm using the same things again now for my redox flow batteries. And so this molecule DHAC, or dihydroxyanthraquinone, was pitched by the Azes group in Harvard, who published this paper in Science a few years ago, showing that they could build a battery out of DHAC and iron ferricyanide on the other side. So this is an inorganic iron 2, iron 3 couple. And so we got into this field because of its more sustainability, and because I like to do different things, and also because it's an obvious NMR problem. And so what we said was, let's just think about now taking this redox flow battery and let's flow the components from one side, and we'll flow them into our NMR machine and we'll see what's going on. And so this is an example where we're flowing the organic component into the NMR magnet. So this is an aqueous system. So the anthraquinone is dissolved into an aqueous electrolyte. And it's going to be, it's called charging because they were charging against the cyanide, but it itself is going to be reduced from the 2- via the semiquinone to the 4-. And we can follow this by NMR spectroscopy. So you start off with 3 peaks, A, B, C. So this is A, B, and C. And what's interesting is when you start charging, or when you start reducing the quinone, the signal disappears, but only B reaches a maximum, and then it goes back again. And then when you get to the fully charged state or the fully reduced state, if you're a quinone, then you see the signals again. So it's now diamagnetic, so you get to see it. So we do DFT. We can look at with DFT where the electrons are, and you can pull out the hyperfine coupling constant. So the coupling between the protons and the unpaired electrons, and this is what's shown here. And you can just see from an electron density map that there's not very much electron density on the B protons, and that's why you can still see it. So that makes sense. I now then need to explain to you this shift. Well, what's sort of interesting is, and this is actually a practical in the physical chemistry lab, is you can take a shift of and you can relate the shift to the bulk magnetic susceptibility of a liquid. So if this is just the water resonance, or this technically it's the HOD resonance because I'm deuterating my electrolyte. And if the local field changes because I have radicals in there, that then gives you a bulk magnetic susceptibility shift. And I can relate that to the susceptibility of the electrolyte, and then I can use that to quantify the number of radicals. And so what I can then do is to quantify how much of this DHAC 3- semiquinone I'm forming. And you notice that it's not 100%. So we're not going via one electron process of this going to this to this. We're reaching a 50% maximum, which I'm showing here, and then it's decreasing. And that's because you've got, let me see if I've lost the slide on this, it's a multiple competing process where the difference between the couples of this reaction and this couple are very close. So once you get to this, you might as well carry on to that. And you have this very complicated equilibrium between the whole two. And by measuring the difference in the concentration of the radicals, that then tells you the difference in the couples between the reactions. And it turns out to be about 30 millivolts. So then you can ask the question, why am I losing the signal? And this is actually due to the fact you get electron transfer reactions in solution, and people know about this in biology, in quinones for many, many years. And that then means that even if you put a small number of radicals into solution, where you get a lot of electron transfer onto these protons, the signal disappears. And we can quantify that phenomena by doing variable temperature NMR. So that's cool. And then once we've done NMR spectroscopy, we can actually then say, okay, well, why don't we just look at the electrons? And so what we do is we take the NMR and we flow it from outside the NMR, and then we flow it, here's the picture here, we can flow it also into an EPR machine. And so this is now following the electron spin. So what you're watching is that electron spin come and go. And then once you've flown it into an EPR machine, why don't you just carry on and just, instead of going back into the flow cell, into the full cell, go back into an NMR machine. So this is now an experiment where we're doing, first of all, the NMR signal, then we're doing, this is the NMR, and so you can see the signal is disappearing, but that's where the EPR signal is a maximum, and then the NMR, and so on. So we can just do this all in a so-called online experiment. And so this is just showing you the same thing now, where you're watching the NMR signal and they're watching the EPR signal at the same time. So anyway, with that, I just wanted to end by saying that it allows you to look at things that are quite important in the field, and that's really how the molecules survive and how they degrade. And we can propose lots of organic degradation mechanisms, which I'm sure some of you in this audience have done organic chemistry, more organic chemistry than I have for many years, but we can all watch this by our NMR spectroscopy. And so with that, I think my hour's up, and I just wanted to end by saying, I hope I've shown you that we can do a lot of different techniques to understand these different materials. And I hope I've illustrated that even a battery that in many ways you think is a solved problem has a lot of really exciting fundamental science questions that need to be answered in order to make materials for sort of the next generation of energy systems that are going to be important for sort of the zero carbon world. And we have to really think about how we do this in the context of sustainability. So it wouldn't be possible without my wonderful research group. This was us a year and a half ago when we were on a group retreat in the mountains in Peak District. And a few people have been listed on the way. Barish Key and Ollie Pesha really got the in-situ NMR to work. Rangeet did the lithium dendrites. Alex, John, Howe, and Nicole did the supercaps. Lot of robot designs to get things to work, and done by Jay and David. NMC work, which is the degradation stuff. I showed you Chow's work, Katerina's work, and Phil. And the redox flow is Evan, Orlando, and Tao. Niobates for Kent and Lauren and John, and Michael and Didi for the DNP, with a lot of collaborators. I think it's the other important thing to stress is none of this is really done sort of by ourselves. It's a very much a sort of international collaboration with people in the UK and in the rest of the world. And thank you very much for listening.
Professor Gray, many thanks for the great talk. And now it's time for the questions. So if you have any question, please write them into the YouTube chat, or you can join the Zoom call if you have registered before. Okay, so the first question is, can atomic batteries be the batteries for the future to be used in the consumer electronics?
Can you spell out a bit? You mean atomic batteries in the sort of nuclear type area? Is that what do you mean? Sorry, could you flesh out what you mean?
There's not more in the question.
Well, maybe the person who's asked the question could just flesh out what they mean. I mean, because I'm not quite sure I understand the question, or maybe just join the conversation. I mean, I think just in general, you have to think about anything that's in the consumer area has to be safe. So that's always a concern. And
then there is another question. what are the most effective ways to reduce the SEI layer? How effective are, for instance, atomic layer deposition techniques?
Well, that's a very good question. The problem you have with an ALD methods, atomic deposition, is that it depends. So you have to create a structure that you can get lithium transport through it. And so a lot of people put on alumina coatings, and they're reasonably good. I mean, if you have a crystalline alumina phase, nothing will go through it. But often these things are amorphous and they work. But the challenge in some materials is you get an expansion and contraction. And so the problem with silicon is that you don't have a stable structure to put an SEI on it. If you look at the sort of graphites of this world, you could think about putting a passivating layer in by ALD. You'd have to do it in a way. Then the next challenge is if you cover the whole thing and it's insulating, you can't get the electrons in. So you have to sort of get the right amount so that you don't increase the internal resistance of your battery. So there's a lot of work on looking at coatings, and ALD is one of the ways. And the alumina coatings, for example, are good because they pick up degradation products like HF and things in the electrolyte. So it's an active area of research. It's also quite expensive, but certainly there's a couple of companies that are working on trying to get it to work and reduce costs. At the moment, it's often just a solution precursor that you then bake on afterwards, is sometimes used on the cathode side. On the anode side, people add extra additives so that they decompose and they form more stable passivating layers. And that's sort of the active area of work. But if you can try and do it intentionally beforehand, then that would in some ways be better because you'd have more control over it to be more like a designer one. But the challenge is getting the right amount of protection without having too much resistance. So thank you for that question. I'm happy to take that or more offline if you're more interested.
And then there is another one. I was wondering how you are observing these battery species during their discharging with NMR. Is solid state NMR needed because the SEI electrodes are solid?
So, I mean, I'm looking at the specific nuclei, and I'm tracking the different local environments of them. And in the in-situ, that's all static. So it's easier to see things that are mobile. If they're very solid and rigid, then you often get broad peaks. But we chose things like lithium metal, where lithium is in a very symmetric environment, and so you get a reasonably sharp peak. In the silicides, the lithium is quite mobile. So I'm watching with the NMR, I'm able to quantify the amount of the different signals, and I'm able to track their environment via the different interactions. So I talked about the metallic interaction, it's called the night shift. So you track, the example I showed was the sodium pools. In the supercaps, I was tracking the ring current effects. In some of the other examples, I was tracking the electron density on the lithium. So when you try and use the NMR, you want to think about what is the interaction and that will be different for the different environments of the lithium ions or the protons in the organic electrolyte example at the end. So you tune your interaction or the way you look at it depending on the system.
There are no more questions, I guess. So, Professor Gray, many thanks for the great talk and for answering the questions. So, and next Thursday, there will be a talk by Professor Anne Ferguson-Smith, the head of the Department of Genetics, University of Cambridge. Professor Ferguson-Smith will be talking about her research in epigenetics. And the talk is going to start at the usual time at 6:15 of the UK time. So thank you for attending the talk and have a nice evening.